Okay, let's start with the last homework. Now I have a constant stream of people coming today to ask about how to balance the electrostatic repulsion in the case of the two particles. I hope the ones who did not came figured out how you do that. But for the sake of everybody, actually the attraction is balanced by the gravitational forces, which in this case act as repulsive force, which has caused a bit of a shock in some people. How can gravitational forces be repulsive? But the idea about this homework is to really make you think a little bit outside the box. So first of all, problems like that are not going to affect your grades, in the sense that I'm not going to make your grade absolute. I'm going to really grade it depending on how well the whole class does. So the idea is not to really try to solve all problems, but the idea is to think a little bit of unorthodox way in kind of why, for example, two particles can repel each other in media. And some people have been very surprised that two particles can repel each other. But again, something that we have been discussing today with some of you. What happens when an air bubble rises in liquid? You can think of this as a gravity, as a Archimedes force, but you can also think of this in terms of gravitational repulsion between the bubble and the Earth, a very large particle, which is mediated by the media, which in this case is water. So a bubble is actually repelled from Earth because the water, the media, is denser than the contents of the bubble. But this is actually a gravitational interaction, so you can have gravitational forces which are repulsive, as you have in the problem of Izraelashvili's, from Izraelashvili's books in this homework. Okay, any questions about the homework, about the similar problems and so on? I have had enough questions actually today. Again, if you feel that some problem is unusual, come and ask me. I'll be glad to help you. But I'll be also glad if you think again a little bit outside the usual and expand your horizons in this class. Now, what we're going to do in this lecture is we're going to discuss van der Waals forces between particles. Until now, we have been discussing what happens between molecules. But in your practice, you're not likely to work with single molecules. You're likely to work with particle suspensions and different types of objects which are going to attract each other because of van der Waals forces. So you would like to know how these particles attract, and you would like to be able to calculate that. This is what we're going to do today. Before that, however, I want to expand a little bit further on a topic that we couldn't finish quite well in the previous lecture. And this is the relation between the van der Waals and the Hamaker constants, the polarizability, the dielectric permittivity, and the refractive index. I won't go into the derivation of this formula, which you can find in the textbooks, and which I certainly don't believe is something that you need to know in detail. What you need to remember is that because the van der Waals forces are dependent on the ionization potential, on the frequency of the electrons circling in the atoms and molecules. Then when you do a very complex integration of all the frequencies in the electrons, in the atoms and so on, we obtain the expression similar to this one for the Hamaker. This is not the way it should work. Frequencies for the Hamaker constants. This is a Hamaker constant. I guess this will need a change of battery soon. This will be a Hamaker constant for the interaction between particle 1 and 3, particle media 1 and 1, between phase 1 and 1, between the media 3. So what happens when you have those two phases interacting with each other across a third media? You can express the van der Hamaker constant by the dipolar polarizabilities or the electric permittivities of the media of the phases 1 and 3, and the refractive indices and of the phases 1 and 3. Now, how do we come to these parameters? The reason is that the polarizability, the electric permittivity, is dependent on the permanent dipole moments of the molecules. If you have molecules with permanent dipole moments, and if you put these molecules inside a constant electric field, these molecules are going to orient themselves along the field. This is how the electric permittivity works. And then, because of, as you know from spectroscopy, because of the vibrational frequency of the electrons, the optical properties of materials are determined by the vibration of the electrons. That's why some molecules absorb light and so on. So the refractive index is actually something which is also related to the vibrational frequency of the electrons, and you can use the refractive index as an estimate of these vibrational frequencies. The bottom line from the perspective of you as users rather than quantum chemists would be that the Hamaker constant can be evaluated by using the electric permittivities, which is measurable by an apparatus, and the refractive indices, which are also measurable by an apparatus. Now, you're not likely to use this method in order to calculate the Hamaker constant, which you can find in a textbook, but experimentally you are more likely to use this method for adjusting the Hamaker constants of different types of phases, which is often the case for polymers in solution, for example. You have two polymers, and you want to have these polymers mixing very well, which means that you want to minimize the interaction between them, or you want to maximize it. If you want to minimize the interaction, you have to do what? You have to, now this term is usually small, so it's usually not important. However, this is always important. So if you want to minimize the interaction, you want to minimize the Hamaker constant. And as you can see here, if you adjust the refractive indices of the two phases to be the same, then these two phases are going to have minimal van der Waals interaction. If you want to maximize the interaction, then you have to maximize the difference in the refractive indexes. So experimentally, this gives you the tool by using something which is as simple as refractive index to be able to adjust interactions in solution or in mixed phases or in colloidal systems. It's a very simple but very powerful technique for different types of colloidal characterizations. And because there are many people here who are interested in polymers, electronic materials, and so on, I have also given just as something that should be kept in mind in terms of physics, how do the dielectric permittivity and the refractive index of different materials vary. You have water here and you have a hydrocarbon. Now, the dielectric permittivity at low frequency eventually becomes an expression that is related to the refractive index at high frequency. Essentially, the refractive index gives you the dielectric permittivity of light when it goes through material, right? Now, as you can see in the case of hydrocarbon, this dielectric permittivity is very straightforward as a function of frequency. If you have a constant field, the dielectric permittivity is about the same as in the visible light region. So when you go up in frequency, you have, this is called static, visible region, UV, and so on. Now, on the other hand, in the case of water, you have this low frequency term, which then levels off, and then water actually at high frequencies has a little bit lower dielectric permittivity, lower refractive index than hydrocarbon. Now, to summarize, let's say, see how quickly you can relate this property of water with all the electronic molecular properties that we have studied so far. Why does water has this specific high dielectric permittivity at low frequency compared to hydrocarbon? Why water has this while hydrocarbon doesn't? Right, yeah. I mean, water has dipole moment, hydrocarbon doesn't have a dipole moment. When you have dipole material at low frequency, it gets polarized because the dipoles orient each other. And this is, on the other hand, one of the reasons why water and hydrocarbon are kind of incompatible, because they really interact with, their molecules interact by themselves in very different ways. Okay, so much about any questions here? Yeah.
So can you mix water and hydrocarbon if you apply an electric field of visible range?
Can you make what?
Can you make them mix when you apply a field of high enough frequency?
Make water and hydrocarbon mix?
Yeah.
I don't know. I don't think somebody has tried that. Perhaps yes, but you're going to hit them so much. I mean, if you want to, what you want to do is you want to kind of, polarize them by the addition of field in the way they interact. This is a very complex molecular question. I cannot quite answer this way. We're going to study some dielectric effects later when we come to the dielectrophoresis, but not on the visible range frequency. Now, one example of how you can manipulate actually matter by using permittivity and static constant in the visible range is so-called optical trapping. Have you heard about optical trapping? I see that some people have. If you have a hydrocarbon droplet in water, for example, you can trap it by an optical beam because it's more permeable, kind of more permeable than light. It has higher refractive index than water. We're going to possibly mention this technique a little bit later on. Daniel, and let's move on.
I'm not sure I'm getting the point.
Uh-huh.
I mean, if this were an experiment, would you be shining a light source on these materials and then measuring the dielectric permittivity?
Well, yeah, I mean, again, like in many, usually, unless you work with dipole materials, you don't need to measure the dielectric permittivity. You just measure the refractive index because this is the major component of the van der Waals force.
Yeah.
It measures the real dispersion component of the interaction, not the dipole interaction. So if you have just, let's say, two polymers, you know that they don't have large dipole moments. Now, you want to make these polymers as mixable as possible. This means that you have to minimize the van der Waals constant of interaction so they don't separate. Now, obviously, if you start mixing them, you can't adjust too much. But while you are synthesizing them, you can measure the refractive index, and you can say, well, I mean, do I have high enough refractive index for this polymer to be mixable? Or should I, for example, add some groups which are going to change the refractive index so the two polymers have the same refractive index? So you can use this as a predictor at the synthesis stage in order to, for example, to synthesize two polymers which are going to mix. Or you can have samples of polymers, and if you want to pick the two which mix better, you can measure the refractive indexes and then pick the couple which have the smallest difference in refractive indexes.
So the dielectric permittivity of water will change if you put a low enough frequency light source on it.
Well, it's okay. That's a complex question. Let's keep that. I mean, like we don't discuss really how the dielectric permittivity is going to change if you apply a field. What you do here is you're measuring the dielectric permittivity and you're measuring the refractive index.
How do you actually get to this graph? Like, how do you get this graph of dielectric frequency, dielectric?
This is an experimental graph.
So you measure different.
Right.
Like.
You start measuring. You can't measure it in a single apparatus
So
unless.
Do you pass on like a different light to the medium so that you
Sure.
have different frequency? And
Absolutely.
then measure the current across it.
Right. Well, I mean, you start here. What you do on the static part, you essentially, this is a capacitance measurement. You put the material between the two plates of a capacitor, and you measure the capacitance. So you start measuring at zero frequency, then start increasing the frequency. You reach somewhere in the gigahertz region and you cannot measure capacitance anymore. So then you switch here in this region, you switch actually what you're going to do, you're going to measure the transmittance and refraction of microwaves. You reach this region, you put it in the, already you are happy here in the visible region. You put it in the, refractivity meter, and you measure the refractive index. The refractive index is equal to the squared, the squared refractive index is equal to the dielectric permittivity. So you have here, this is plotted in terms of dielectric permittivity, but this is also equivalent to refractive index. And then when you get to here, I mean, you really don't want to measure that. It's too high frequency, it's X-rays and so on. So this is a complex composite graph which people have constructed by many different techniques. Okay, this was really a little bit of a detraction from our class. It's not related to colloids, but I hope this will be important and this is going to help us when we study dielectrophoresis, all types of polarization effects. Okay. Now back to van der Waals and back to colloids, back to formulas which we can derive, unlike the formulas that we can derive like the previous one. Now this is just a reminder what we're going to do here in the whole lecture. We are going to integrate pairwise the interactions between small volumes of two bodies by using the van der Waals potential, so we can eventually derive the total energy of interaction between these two bodies. We know how molecules interact with each other. Now we have to integrate over the whole value of the whole volume, all the molecules that are present in the bodies, in order to derive the interaction between two particles, two phases, in thin films, and so on. And the basics of how to do this integration is shown here again. We integrate over the first volume, the volume of the first particle, the volume of the second particle, the van der Waals constant divided by the distance between the two particles, which is usually the squared coordinates, the square difference of the coordinates between the two particles. And what may appear in front is the Hamaker constant, where we have the van der Waals constants times the two densities and times p squared. Now I'm going to go through many formulas. I have shown the derivation for your information, so you don't feel that I'm kind of trying to sell you here something which you don't understand. So the idea from this class is not that you should remember those derivations. I'm going to forget them in a couple of days myself. The idea is to remember physically how you do that, and then the idea is to understand how the simple formula that we arrived at are derived. We're going to come to very simple formulas which are no more complex than the formulas which you have studied in high school physics. So the applications of what we're going to study here is very simple. I want you to understand the physics, but I want you to be able to apply the simple formulas which we're going to derive. And the first thing that we need to derive, the first formula, is an interaction of a single molecule with a large phase. You can consider this phase as being semi-infinite. Now this single molecule is going to interact with all the molecules in this phase. So we have to find a way of integrating the interaction over all molecules present in the large phase. Now what do we do? Of course we do some, first we start with the differential volume, and then we integrate this differential volume over the volume of the whole phase. Now it is convenient to work in radial coordinates. So what we do is we consider a differential ring. The volume of this ring, shown here, so you can imagine of the ring being like something like this, would be 2 times pi x. In this case is this coordinate. You can't see too well, obviously. And then z is the vertical coordinate here. Oh, sorry, z is, excuse me, z, this is the z coordinate, and this is the x coordinate. So dz times dx times 2 times pi is equal to the volume of this ring. If we go through all coordinates, kind of move this ring throughout all of the body, we're going to find the interactions. Now, the number of the molecules in this ring is going to be this same volume multiplied by the density. In this case, the density is expressed as molecules per volume. Now, the interaction between a molecule here and the molecule in this ring is going to be equal to the van der Waals constant divided by the distance between the molecule and the molecule in the ring on the 6th power. This is the basis of what we have been deriving so far. Now, this distance in this case is going to be equal, this is this side of the triangle, this is x, this is z. So this side of the triangle is equal to r squared plus x squared, and then you take the square root of that. Simple geometry. So we can replace the distance here with x and z, and then we have to integrate. Now, we put all of this in the integral. We have 2 times, this is the volume, times the density, the 2 running coordinates, times the interaction, which is the van der Waals constant divided by x squared, z squared, and all of this is on the power of n over 2, because we have n is in this case is equal to 6 for the van der Waals interaction, but this formula has been derived for the case of interaction which can be on any power dependence. We put this in here. This is just show how you do the integration. You substitute you substitute the variable here at this point, and then you obtain this formula which tells the energy of interaction as a function of the distance between the molecule and the surface is equal to 2 times pi, the van der Waals constant, the density. This is going to be, you have to replace n with 6 here, the distance to the n minus 3rd power. Now, what are the boundaries of integration? The integration is from the distance between the molecule and the surface to infinity. And in this case, from x equal to 0 to infinity again. We do the integration. We obtain this formula. We have used here the general expression for any types of force, which is dependent on the distance between the molecule and the power of n. And for the case of van der Waals interaction is equal to 6. We substitute this, and then we end up with this very simple formula. This is what I like here. That the interaction between a single molecule and the semi-infinite phase is equal to pi van der Waals constant density divided by 6 times the distance between the molecule and the surface on the 3rd power. The first thing that you can see here is suddenly this interaction is already not that short-ranged. Why is it not that short-ranged? Because this molecule interacts with so many molecules that even if you take it further apart, it still has considerable attraction towards the face. And then, so we have eventually a molecular interaction which is dependent on the 6th power of the distance, being replaced by a molecular phase interaction which is on the 3rd power of the distance, macroscopic interaction. We have derived this formula. We're going to use it right now, but this is really very simple. It's a little bit difficult to explain because of all the math that's involved. So I'd like to answer questions so you're really sure that you understood what's happening here and why you're using this formula.
I just wanted to, I think you left out an equal sign on the top. At the interaction.
Here?
Yeah, it should be.
Oh yeah, that's equal, yeah.
Equal minus.
Yep, right. Right. Please correct in your right hand. That is equal. And why do we have divided by 2? It should be equal minus. Why is it divided by 2? Because we have the square root from the calculation of the distance. We have the two coordinates, which should be a square, which we should take the square root. So it's a kind of mathematically, it's an integration procedure. Obviously, we have to do mathematical tricks in order to do the integration. The point, however, is that when we substitute everything, we just have this simple formula for interaction between a molecule and the same infinite phase. So anytime you have a molecule in vacuum, for example, interacting with the phase, you know how to calculate, to use that. Now, you can say, well, I mean, that's not very useful, but this is really just the first step. And you can see now the power of this formula that we have derived, because from this formula, we can immediately derive the formula for interaction of macroscopic bodies. Now, what happens if we have two semi-infinite media interacting across a thin film like that? And this is very important colloidal problem. For example, we have a foam film. You have two air phases interacting across a water film, or the other, or the vice versa. Or practically, you have what happens when you have a saran wrap wrapping around a pot, for example. Why does a saran wrap stick to a pot? You have a large phase which interacts with the third phase across air. So how do you calculate interactions in thin films? How can you calculate such interactions? Now, first of all, we have to do interactions per unit area. Why don't we do interactions between infinite phases? Because if the two phases are interacting across a thin film are infinite, then the interaction itself is going to be infinite. Right? The interaction is depending on the area of the phases. If we extend the area to infinity, then the phases are going to interact with infinity. So we calculate the interaction per unit area. So we take one phase with a surface of unit area and we approach it to the other phase. The distance between the surfaces of the two faces is d. And then we have to do the integration only in one dimension. We have to integrate how these molecules interact with these molecules. Now, we already know the energy of interaction between a single molecule and the same infinite phase, which we derived from the previous slide. So then we can use this energy in order to calculate how each molecule inside this second phase is going to interact with all molecules from the other phase. So we just have to take the formula that we derived from the previous on the previous slide and apply it for all the molecules in here, and then we're going to find the energy of interaction. If you take a differential slice out of this second phase, the number of the molecules in the slice would be equal to the area times the density times the thickness. I have put the areas in bracket here because we already worked with an area which is equal to unity. So then the interaction of each molecules in the slice would be this one, which you already know. So what we have to do then is we have to plug in this formula in the energy of interaction, and we have to integrate from a distance d to infinity, by which way we are finding the interaction between all molecules in this phase and all molecules in that phase. We have ρ1 and ρ2 emerging here, the density of this phase, the density of that phase. What we have remaining here in the integral is dz of z to the third power. This third power comes from the third power which we derived from the previous slide. We integrate it from here to infinity, kind of in a way move this slice all through the other material, find the energy of interaction, and we obtain this formula, which is pi times the van der Waals constant, the two densities divided by 12 times d squared. it is convenient to put in one more pi on the bottom here, so we have the Hamaker constant on top. And you can see that all all those calculations for like 3 consecutive lectures, how we start with molecular energies, expand them to different types of interactions, expand them to solid body. All of those lead us to some very simple, very practical formula, which tells us that in order to calculate interactions in thin films, you need to know the Hamaker constant, the distance between the thickness of the film, and that's it. You just put it in this very simple formula and you calculate the energy of interaction in the thin film. So again, if somebody tells you that calculating interactions in colloid science is difficult, don't believe him, because you can see that this is simple. I'm a little bit misleading you here because you have to take into account the electrostatic interactions, which we're going to do a bit later. But you can see that van der Waals, all those complex formulas, all lead to some very simple expressions which are easily usable. You need to know the Hamaker constant, but we discussed a few ways of knowing and getting to know the Hamaker constant. Any questions here? Okay. So, of course, we don't always work with flat phases. We sometimes work with particles. So how do we calculate the interactions between the particles? I have skipped the calculations here. I have just given you the idea. Eventually you start with a slice of the sphere. Calculate the interactions between each molecule of this slice with all the other semi-infinite phase. Do the integration by putting again the energy of interaction between each molecule and the semi-infinite phase which we derived previously. Do the mathematics here. After you do the mathematics, you can actually arrive at 2 expressions in 2 limiting cases. The 2 limiting cases is if this distance is small compared to the radius. In the other case is if this distance is large compared to the radius. So in the first case, we have let's say a large spherical molecule being very close to the surface. And in the other case, we have a small spherical molecule being very far away from the surface. Very simple formulas. Hamaker constant, radius, 6 times the distance between the sphere and the surface. In this case, we have something that is actually a Hamaker constant too. Six times the distance on the 3rd power, the volume of the molecule. In the intermediate case, you're going to have more complex formulas. These are really the formulas which are derived by neglecting some terms. You're going to have more complex formulas, but nothing that you cannot sit down and program in your computer in half an hour, for example. So if you want to calculate, and this is an important problem. This, for example, is the problem of adsorption of particles on a solid surface. How do you want to calculate the strength of the adsorption of the particles as a function of the distance, as a function of the particle size, as a function of the Hamaker constant, the material in the particles and in the surface? Now, again, the question kind of which makes you go back and revise some material a little bit. Now, what does this formula remind you of? Something that we just derived.
Interaction between a particle and a semi-infinite.
The interaction between a molecule and the semi. Yeah. Actually, you can see that it's the same. Instead of a molecule, you have here volume times density, but the distance dependence is the same. It's to the 3rd power of the distance. Now, why is it the same? Because in the limiting case where we have a small molecule, small particle far apart from the surface, the interaction is really physically very similar as a single molecule on the surface. So a small particle far away from the surface would have the same dependence of the interaction as a molecule, a single molecule away from the surface. So we have the same dependencies emerging over and over and allowing us to calculate this. So let's summarize here on this slide. Van der Waals energy of interaction between objects of different shapes. We spent lots of time in order to understand how two molecules work, but we know that the interaction is dependent on the 6th power of the distance. Two spheres, this is the general case when the spheres have non-equal radii. But again, it's a simple formula which can be derived following similar integration that we did. Now, we did not derive it here, but it's really a mathematical problem rather than real physical one. This is the formula which we derived first in order to derive this formula and that formula. And then people have derived other expressions to parallel chain molecules. What is this useful for? For polymers, for example. Two cylinders oriented like that. Two cylinders oriented in this direction. You can see that all those formulas are just simple formulas which include Hamaker constant, radius of the particles, the cylinders, and distance. So something that we can immediately use and really not that difficult to use. Okay, any questions so far? I would assume that the lack of question is because, I mean, you have understood everything and you know how to use it from now on. So this is the first part of what we have to study. Now, obviously, if you have repulsive, outly attractive interactions, this is not enough in colloids. So we're going to study the repulsive interactions a bit later. But this is really the basics of all interactions related to repulsive potentials, type of Van der Waals type. Now, just to demonstrate the power of what we have studied so far, of how it can work, we have this nice formula for the interaction between two parallel thin materials. Now, let me demonstrate something that's beautiful in its simplicity. How we can immediately use this formula in order to derive something that's very usable, simple, and physically meaningful. Now, the formula tells us that the interaction between two semi-infinite bodies would be equal to the Hamaker constant divided by 12 times pi times the distance between the two surfaces. Now, however, you know that all materials are made of molecules or atoms. Now, how about then if we think about what happens if we take the surfaces between two planes of atoms, calculate the energy of separating these two planes of atoms and then taking the material apart. We can use this formula actually to calculate what is the interaction between the cases where we have the two surfaces in molecular contact and then being separated. And this is a basic problem in adhesion. And actually this leads to splitting the material into two pieces, and each piece has a unit surface area. So this is an adhesion problem. If you remember, the adhesion allows us to calculate the surface energy or the surface tension of the materials. So we can take this formula. We can say, okay, the difference in the energy is going to be the energy when the two surfaces are separated minus the energy when the two surfaces are in contact. We can take some parameter for the two surfaces in contact, which would be comparable to the intermolecular distance. assume that we take them far apart, creating the two surfaces. If we take them far apart, this distance is going to go to infinity and this term is going to be 0. So all that we are left for the energy of splitting the two surfaces apart would be equal to this term, which is minus the Hamaker constant 12 times pi d0 squared. And this term in itself is going to be equal, actually it's going to be plus because we have a minus here. In this term, and this tells us what? That we have to spend energy in order to do this process. Surfaces would never split themselves spontaneously. This is energy which we need to make. And this is going to be equal to 2 times the interfacial tension. Because we have created two surfaces of interfacial tension or interfacial energy, right? And this gives us the relation between the Hamaker constant and the interfacial tension of materials. So in the beginning of the class, I told you that you can calculate Hamaker constant by measuring refractive indexes and so on. But as you can see now, you can, in many cases, calculate Hamaker constant by measuring the interfacial tension. And people have actually found out that there is a universal intermolecular distance, which works very well. It's a bit smaller than the distance between two atoms. And the reason it is smaller is that the atoms in the material are not situated in exactly split planes. They are a little bit intermingled and closer than just being in the material, being in planes. And then this is actually, if you have to do calculations, I'm going to include the smiley sign here. This is a simple formula where the Hamaker constant is expressed in joules and the interfacial tension is expressed in millijoules per meter. The units that we usually use when we work with Hamaker constants and with interfacial tensions. Millijoules per, it should be, millijoules per meter squared when it's millijoules. It should be, actually should be millinewtons per meter, the way I like it, but millinewtons per meter. Okay. So, which are the, okay, let's start asking some questions here again, like a response. Now, which liquids would you expect this to work well, and for which liquids you wouldn't expect this to work well?
Non-polar liquids.
Are the ones where it works or doesn't work?
Where it works.
Right. I mean, that's an obvious question. And I'm going to show you the results right now. Now, another question here. This is a little bit more it's even simpler, actually. Now, I have shown here the energy as the difference between the energy at contact and at separation. Now, you have seen all those expressions where people, this is a little bit of a trick question, actually, where people do integration over the all distances of separation. Now, why can we take here the energy in the first case and in the second case without integration? It's a bit of a trick question. So, why didn't we do integration over the distance here?
Because it cancels out with the molecules that are pulling in the other direction.
No, I mean, I thought this is a trick question. This is really a question to...
Path independent.
Huh?
Is it because it's path independent or not?
No. This is something simpler than that. I mean, it's a trick question. Again, think why don't we have integration here? Why just we subtract the energies?
Subtract the energies.
What we do here is we subtract the energy when we separate them and the energy in contact, and we obtain the energy for separation. Why don't we do integration over the range of distances between the planes?
Because once you separate them, you are not separating it any further. Once you
Well, yeah, I don't care how
already
further you
created
separate it. No. The answer is something simpler. The answer is you should tell me no. I mean, don't try to trick us here.
You mean why don't you integrate over each
Distance.
increment of distance?
Right. Why don't you do integral over the distance here?
Because they would each one would cancel each other out, right?
Maybe, but I mean that's not exactly what I had in mind. Now, in which case do you do integration? Let's put it the other way. Okay, I got you on a thermodynamic question, but it's very simple. When you calculate energy, you only need the initial and the final stage of the energy. You do integration when you calculate the energy as a function of a force. So when you have a formula for the force, you have to integrate the force, pressure, whatever, over the whole range of distances, right, to obtain the energy. But when you have the energy in the initial and the final stage, the energy, you know that for a thermodynamic process, you just need the difference in the energy. You don't do integration when you work in the energy coordinates. You do integration when you work in the force coordinates. So, I mean, just physically, the answer to my question is you don't need to do integration. I would integrate if I worked with the forces. We have integration here because we're integrating over molecules, not over the number of molecules. We're not integrating over, let's say, distance of approach and so on. So this is integration over volume, in fact, not over distance. So, and of course, somebody mentioned here, the more power the molecules, the larger the deviation between this formula and the reality. This is a summary of the theoretical Hamaker constants for a range of liquids. The calculated Hamaker constant, the calculated interfacial tension or energy from the formula on the previous slide, and the experimentally measured value. You can see that in many cases the correlation is excellent. Hydrocarbons, non-polar molecules. In some cases it's not that good. Glycol, which is polar molecule. And in some cases the correlation is outright disastrous. Water or peroxide, where we have, you know what the reason is. We have hydrogen bonding, so obviously the formulas are not valid there. That's it. But it's a very simple formula, and it immediately allows you to understand so many things in colloidal science. And this ends the interaction part of our lecture. Now we have to understand a little bit about forces. Now forces are, you can either work with interactions or you can work with forces. Now how do we obtain the forces? Well, you can tell me, we can take the formula for the interaction and we can differentiate it to obtain the force. In some cases this is possible. In cases of more complex objects, it's not immediately possible. So people would like to make some simple correlation between forces and energies, which is not really derived by differentiation of expressions which you may or may not know. And that's why Deragin, the famous Russian scientist, has derived an expression which is very widely cited, which relates the distance between two spheres and the interaction, the force between two flat surfaces. So what you want to do is you want eventually to derive the correlation between the interaction between two spheres and the interaction between flat surfaces. So you can say, I know what happens between flat surfaces. I have spheres, I can immediately apply whatever I have here to the interaction between spheres. So this is a very well-known formula. It takes lots of math to derive. So I'm going to do this right now, but I would really like to just kind of try to explain here what happens. Now, just for some kind of a little bit of a refreshment here, you heard about Deragin or who he was and so on? Now, he was one of the founders in the colloidal science in Russia, the Soviet Union. He worked independently of the US scientists at that time, so finally it came out that when it comes to colloidal forces and so on, they have pretty much made the same theory, both in US and in Russia. So this is the so-called Deragin-Landau-Verwey-Overbeek theory, which we're going to study a bit later. Apart from that, Deragin was a very kind of autocratic scientist. So he was the boss. And he was alive when I started as a graduate student, actually, but he was more than 90 years old. Now, he has such a kind of strong motivation that actually, even though he was more than 90 years old, he still would like to go to conferences and present results and so on. Now, the problem by this time was that actually, and what he complained actually, was that, so he started with, so he became a professor, researcher in the Russian Academy of Sciences. So he had his graduate students. His graduate students became his assistants and collaborators. He was still the boss, but they became his collaborators and so on. But then by the time he became 90, his graduate students, most of them had either died or retired. So he didn't have assistants just because he was so old that his assistants already had died or retired. The first international meeting to which I went actually was organized by my advisor. And Deragin had signed up for an invited talk there, but he couldn't come for health reasons. And yet he still wanted his talk to be heard at that meeting, so he sent his lecture notes. So the notes had to be read by someone, and I was almost about to be kind of called to be the person who reads Deragin's notes. So my first presentation at the conference meeting might have been Deragin's presentation, but I kind of managed to find my way out of that actually, and somebody else did this. Anyway, he has done lots for colloidal science, and his contribution in this case is to actually do the following. Now you have the force between flat surfaces. What you can do is you can eventually integrate the force over the surface of the two spheres. So you can say I'm going to see how this patch of the spheres interacts with the surface of all the other spheres. So eventually this is an integration over surfaces rather than integration over volumes. And the force then would be equal to the area times the multiplied by the force divided by the area. So eventually the area would cancel. So you're going to have an integral of the force between the two spheres. So if you do the integration in this way, you're going to derive the force. What he has done, however, is he has said, I'm going to take not the integral of the force, which is difficult to find. I'm going to have an integral of the area times the derivative of the force with respect to the area. And this force with respect to the area, now the force here, because you have something that's so thin, you can consider the interaction between these two, let's say, surface rings as being an interaction between two flat surfaces. So you say, I'm going to do differential summation over the surfaces, and because I do this differentially, all the interaction I'm going to do is going to be expressed by the force between flat surfaces. I just have to find the appropriate expressions for derivation of that. And then what you need to do is you need to find the coordinates. Now you need, let's say you have these two rings. So this ring interacts with the other ring across the gap. You need to have the distance z here between the two rings. Now this distance would be equal to the distance between the particles plus this small distance z1 and z2 here. From here on it becomes just approximations by using simple geometry, which you can follow. If like won't go into details. You can express this through the radius of the curvature and through the sides of the triangles. Eventually simplify this because this is the most important term. And eventually you arrive at the expression which tells you that the distance z is equal to the distance between the particles plus this term here, where you have the radius of the particles, and x in this case is the vertical coordinate. So if you integrate in vertical distance, you are going to obtain the force between the two particles. In order to use this expression here, you have to differentiate, so you obtain the dz as a function of dx. In this integral here, you have dx, so actually you express dx as a function of dz. And then you substitute into this integral. The next slides give you all. The next slide gives you all of the kind of the steps of the derivation. I'm not going through all of these details. You have the force between the two surfaces, the integral. This is what came out of the geometrical consideration. The force between two flat surfaces times dz. The integral is over z equal of d to z equal to infinity. So you start up with an integral which should have been in this direction, but because you express in the x direction, but because you express x over the z direction, so you end up with replacing dx with dz, and you integrate over dz.
About the last one.
Here or this one or that one?
What are the big Z1 and Z2?
The big, it's actually, if you take a look here, it's all on this figure. The big z is this distance here.
Yeah. What about big Z subscript 1?
It's the same as
You have small z subscript 1, z1 and z2, right? This one.
Those are the same.
Oh, okay. So.
And this z1 and z2 are actually these small chunks of distance here between the surface of the sphere and the ring. So you just have z1 here, z2 here, d is the distance, the large z, the distance between the two rings. It's just geometry. And I've never remembered for long how to derive this. I could possibly derive it if I sit down right now, but I'm going to forget it in a couple of days. So this is, I would like you to understand how you can do integration in case you need it to. But this is not something that you're going to have at the test, for example. What you're going to have at the test, however, is the application of the formula, which I'm going to derive right now by following this. What I want you to understand, however, is how this works. So we have arrived at this formula. We have force here. Now, what we could do is we could say, well, the force is the derivative of the energy, so we can replace this here with the derivative of the energy with respect to the distance. And you do essentially a third substitution where the integral is actually happens to be an integral over the energy from z equals to d to infinity. And this immediately, kind of like when you integrate, having in mind that the energy is actually at infinity is 0, you immediately obtain this simple formula, which is the Reagin's formula, which tells you that the force between two spheres is equal to this term here, which is just the radius, includes the radius of the two spheres, and the energy of interaction between flat surfaces. And why is this expression important? Because if you know the energy of interaction between flat surfaces, and you already know it, you can immediately derive the force of interaction between particles, which we don't know yet. You don't need to do differentiation. You don't need to understand the dependence of the force as a function of the distance. You just plug in the expression for the energy and you obtain the expression for the force. And here are just some of the cool things that you can do with this formula. Now, if the two spheres are equal, you have a formula which is even simpler. The energy of interaction, the force between the spheres, is equal to pi times the radius of the spheres times the energy of interaction between flat surfaces. if the two spheres touch each other, you can replace the energy here with 2 times gamma, which is the adhesion energy. And then you obtain immediately the adhesion energy between two spheres, which is a very important formula if you are working with powders, for example. And if you want to understand how you can calculate the adhesion inside your powder, or in case you have different types of particles which you want to separate apart. Now, you can take this expression in its limit, where you have one of the spheres eventually being infinitely large. In the case of an infinitely large sphere, it's eventually a flat wall. So immediately you obtain the force of interaction between a flat wall and a sphere as a function of the energy of interaction between two flat surfaces. And finally, something that's important in measuring these forces, you can calculate by some additional derivations the force between cross cylinders, where R1 and R2 are the radii of these cylinders. Now, when you look, so this is the force between two cylinders, this is the force between a flat surface and a sphere. Now, when you look at these two formulas, do you see some resemblance? They are essentially the same. If the radius of the cylinders are the same, then the force between the two cylinders is going to be the same as the force between a sphere with the same radius and the surface. So the force between two cross cylinders is equal to the force between a sphere and the surface. And this is very nice because it allows us to measure colloidal forces by using microscopic bodies. So much about the forces here. So right now, we're done with the formulas for today. Right now we know how to calculate energies, we know how to calculate forces. You don't have to remember all the derivations, but knowing where to find these formulas in a handbook or in a textbook, you can immediately calculate forces between particles, cylinders, thin films, all types of objects that you need for your research. You know how strongly they are going to stick to each other. This is not the whole set of knowledge you need to know in order to understand colloids, because what would happen if all the forces in the world were attractive, as in the van der Waals case? I mean, obviously, everything would be a large pool of goo, and that's not the case with us. So something keeps the things apart from each other. And this something is the electrostatic interaction. We're going to study this a little bit later on. As a conclusion of this lecture, just some slides which demonstrate different effects which can be explained by the phenomena that we studied so far. Adhesion of particles to surfaces. If you don't work in electrostatic environment, like if you work in oil or in air, you know how to calculate that already. Adhesion of thin films to surfaces. The force that you need to peel off a thin film from a surface can be calculated by the formulas that we use. Different types of interactions between suspended objects and so on. Now, this is an experimentally important case because if you want to measure the interactions, you have to design some apparatus which is going to bring surfaces close together, and then you measure the force. Once you know the force, how are you going to calculate the interaction? By using what? If you measure the force, how are you going to calculate the interaction? If I'm asking you something, this means that you have to go one slide back. You know the Reagan's approximation for the relation between force and energy. You don't have my favorite expression, energy meter, but you have force meters in your lab. So if you measure the force between objects, you can calculate the interactions between objects. And I'm going to show you how is Raleigh actually made this possible. You can calculate contact angles of liquids on surfaces because you now know how the liquids are going to interact with the surfaces. You can calculate the thickness of free liquid films, such as foam films, or films, wetting films on a solid surface. And you know why in some cases these films would try to thin, and in some cases, rare cases, these films are going to try to thicken themselves. You can calculate the force between different types of colloidal suspensions, whether they be latex spheres, proteins, nanoparticles, biomolecules, whatever. Again, with the disclaimer that you have to calculate the propulsion, which you're going to study a bit later, starting from the next time. You can measure properties of colloidal suspensions. You can explain different types of osmotic effects, why particles would like to be more hydrated in some environments than other environments. Just a couple of the words of how people have been measuring these forces. Raleigh has made his career by making popular an apparatus which actually brings two cross cylinders towards each other by a very precise, essentially we have a set of very precise springs and balances which brings the two surfaces, cross cylinder surfaces, together. You can measure the distance between the separation between the surfaces optically by using interference. So this has been the first apparatus which has allowed precisely to measure different types of interactions between surfaces and to compare them with theory. Now, he tried to commercialize that, which was not a very good idea perhaps, because in the meantime a couple of physicists from the IBM laboratory in Switzerland invented what? AFM. And you have heard about AFM. We're going to discuss this a little bit later, how it works and so on. But AFM essentially works on measuring the displacement on a flat tip against the surface. But the displacement of this tip is going to be a function of the intermolecular interactions. So essentially any AFM is a very precise instrument also for measuring interactions. And you can actually scan the surfaces. You can, what people routinely do these days, you can actually kind of attach a particle on the surface of the AFM and probe the surface with the particle and measure the interactions. So these days people can really measure interactions on a microscopic scale by using atomic force microscopy. So this has become from something that has been the cutting edge of science just a couple of 20 or 30 years ago. Now it's more or less routine measurement if you need to do it. And this is the end of my lecture. Again, you have the summary slide. I won't go through that. I would recommend that you go through that yourself just to remind what we have studied so far. We have a couple of minutes yet, so if you have any questions, now is the time to ask. Now this also concludes the end of the material that's going to be included in the first test, which is going to be Thursday next week. Now, would you like that so for the distance education, the students are not going to have a lecture on Thursday next week, but we're going to meet with you to make the test, which is going to be in Riddick. Now, would you like to change the time to another time, actually, or 6 o'clock on Thursday is okay for you, for the test? I think it's a good time, kind of quiet and so on. So the test is going to include all material so far. You can imagine what the test can be like. I'm not going to give you problems like the gravitational repulsion that we had today, but you have to have a good grasp of all those simple formulas that we have been studying. You can see that we can have very complex theory, but this theory, at least in colloids, always leads us to something that's very simple and usable. something that you can write down on a sheet of paper and make the calculations yourselves. Okay, last chance for questions. Okay, well, let's finish here. Thank you.